Hello, good morning. Can you hear me? And do you see the screen?
Yes.
Okay, thanks. Okay. Okay. So I think that last time we were deriving the so-called canonical ensemble. Just a short summary. So what we did is to consider a system, a large system that we call T, total T for total system. Then we determined a subsystem S, small, which is in contact with the reservoir. So we divided the total system into two systems. One is a small system, and the other one is a reservoir, with the role of keeping with the role of providing energy to the subsystem S in order to maintain the temperature of S constant. Okay, this is the situation. So now, differently from the microcanonical ensemble, where the system under study is isolated, so it has a constant number of particles, constant volume, and constant total energy. In this case, the situation is different in the sense that our system, the system to which we are interested in, can exchange heat with the reservoir in such a way that its temperature is constant, okay, and is equal to the temperature of the reservoir. The reservoir can act as a reservoir because it has a very large heat capacity. Okay, so it's a large system, and therefore it can exchange energy without having any variation of its temperature. Now, at some point, we said, okay, let us compute which is the distribution function for the subsystem S under the hypothesis that we integrate over all the degrees of freedom which are belonging to the reservoir. Okay, and then at some point we arrived at the following form, in which d omega s, which was integrated over the degrees of freedom of the reservoir, let me write it down, integrated over the reservoir degrees of freedom, now this phase space volume for the subsystem was equal to rho, now which is called the canonical ensemble, which is differently from the previous case, so the case of the microcanonical ensemble now is a function of PS and QS. So in principle, this is a function of all the variables or the coordinates and momenta of the subsystem. And here I have dQs, dPs. And then we say that this rho was actually equal, this was derived by applying the entropy formula, the Boltzmann entropy formula to the reservoir. We said that rho is equal to e to the minus es divided by kBt, and we normalized with respect to 1, so therefore we had e minus es divided by kBt dqs dps. Okay, now this is called canonical ensemble, and let us remove for the subscript s, and let's write in the following way: remove subscript So we say that rho is equal to e to the minus. Now here I can write without any different, without any, without making any error, I can write the energy or the Hamiltonian, which at the classical level are the same quantities. So I can also write e to the minus h beta, where beta is 1 over kBt. And here I have the integral dq dp e to the minus h beta, where h is the Hamiltonian, which coincides with the total energy A, mechanical energy of the subsystem S. Okay? Now, in principle, here in this integral, we will specify this later. I have to integrate over all the momenta and coordinates of the particles belonging to the subsystem S. Now we are not distinguishing anymore between subsystem and reservoir, so we just concentrate on, we remove the subscript and we concentrate on our subsystem. Now you see the difference with respect to the previous ensemble, which was the micro-canonical ensemble. As I said before, rho, now this time is not a constant, as in the case of the micro-canonical ensemble, but it is a function itself of all the coordinates and momenta of the particles. Okay, so let me change page. And so we are here. So rho, now in this case, is a function of all q and p, and it is provided by the formula that I just removed, that was this one. Okay. Now let me make some comments about this. First of all, remember that we wrote at some point an equation which was the Liouville equation for the distribution function in the phase space. So, and we said, okay, under the stationary condition, d rho dt equal to 0, which is stationary condition, which means thermodynamical equilibrium, basically. For the Liouville equation, we need the Poisson bracket between rho and h to be equal 0. And we said last time, in the case of the microcanonical ensemble, that this equation is solved trivially by taking rho constant. Now, in this case, it is also respected, since rho is just a function of h, as you see from here. And therefore, if you do the Poisson bracket between h and a function which is just a function of h, then you can show by doing the exercise that the Poisson bracket is equal to 0, just because rho is a function of h. So when you derive rho with respect to p and q, you just make a chain rule, and then you will see that the result is equal to 0. So again, this ensemble indeed can be used in stationary condition, which means thermodynamical equilibrium, because it's just a function of h. So it's another possible solution to the Liouville equation in stationary condition, which means thermodynamical equilibrium. Which is the interpretation of rho? Now, in the microcanonical ensemble, basically it was corresponding to the probability for a state to be, well, it was basically, once you fix the constraints of energy, volume, and number of particles, basically is this probability was constant in the microcanonical ensemble, constant in the volume in which rho was different from 0, and it was 0 outside of this volume. Okay, this was the interpretation. So it's a probability which was basically 1 over the volume in which the rho was different from 0. Now, in this case, is not a constant, as I said before, but is an exponential e to the minus h beta, and basically is the probability that the system, by system I mean the full system, so the full system, not one particle, has an energy between E and E plus dE. Okay, where E and H are the same function, basically, okay? Now, consider the fact that this is the total energy of the system, is not the energy of a single particle. So we are considering our system in its full glory. The system could contain free particles or particles with interaction, or it could be an external field. Anyway, there is an energy associated with the system, and the canonical distribution function provides the probability for the system to have an energy between E and E plus dE. Okay. Now, it's very trivial at this point to define the average energy of our system, where the average is over the canonical ensemble, and I remind you the ensemble is basically a collection of systems which are mental copies of our system, and they just have different microstates, but which are anyway compatible with the macro state. Okay. Now, if we average over the points over the configuration of the canonical ensemble, the average energy can be defined as follows. Here you have dq dp. Here you have e to the minus h beta, and here I have h, or e, which is the same. Since in any case e and h are the same function. And here I have the normalization dq dp e to the minus h beta. This is the average energy. Okay. Now, here consider that A equal to E, they are functions of Q and P. So they depend on the microphysics, so the position and the momenta of the particles. But when we do the average over the canonical ensemble, that we don't have any dependence anymore from the microphysics, this is the average energy, and actually this corresponds exactly to the internal energy of thermodynamics. Now, there is a difference indeed, and this will be clearer later. There is the difference in this case between internal energy and energy of the system that was not present in the case of the microcanonical ensemble, since the system was isolated. But here is different, because one thing is the energy of the system for a certain configuration, and in another thing is the internal energy that could be that could fluctuate. Actually, we will see that the fluctuations are very small, actually, and therefore the results that we will obtain in this ensemble actually are compatible with the results that we get in the microcanonical ensemble. Anyway, this is the internal energy of thermodynamics, and I can construct the average, the ensemble average of all the possible observable. If I have O, which is an observable, which is in principle is a function of P and Q, the average, ensemble average of O is just, again, as before, dq dp e to the minus h beta O divided by dq dp e to the minus h beta. Okay, so this is the average of over the ensemble of a certain observable O, which depends on the microscopic variables. Now there is a function that we need to introduce, and this is basically the most important quantity here, which is the canonical partition function, which is defined, but for some normalization that will be clear later, but it's basically the following, is the integral of e to the minus h beta dq dp. Okay, so this is called canonical partition function. And as you see, the canonical partition function allows, for instance, to derive the internal energy, which is the average of the energy, the ensemble average, as minus derivative with respect to beta of the logarithm of the canonical partition function. This is easily realized because if I do the derivative of beta with a minus, I get a factor h in the numerator, so I get exactly the same expression as before. Okay. So therefore, this function here, if you want, as we will see, will allow to derive all the thermodynamical variables, such as the internal energy, and represent, if you want, the link between microphysics, because it contains the Hamiltonian and the integral over the Hamiltonian in the phase space, or in the phase space of this function E, and allows to find the thermodynamical variables, which are macroscopic variables. Thermodynamics. Actually, we will see that this partition function, canonical partition function, is related to the Helmholtz free energy. We will see this in a moment. Anyway, once we have the partition function, the canonical partition function, we have everything about our system, in the sense that we can compute the thermodynamical variables, such as internal energy and all the other variables, as we will see, and it allows also to compute fluctuations. And this is actually, for instance, a case in which statistical mechanics overcomes thermodynamics, because within the scheme, one can compute the fluctuations, for instance, the fluctuation of the energy, and also higher order, so what are called susceptibilities. So in principle, in this scheme, one can go beyond the average that are just defined in thermodynamics and compute derivatives, basically, which correspond actually to higher order derivatives of the partition function or the logarithm of the partition function. Now let me consider the following situation. So let's apply this partition function to the case of a system of just one particle in one dimension, which is of course in contact with a thermal reservoir, no? Because this is the situation described by the canonical partition function or by the canonical ensemble, in contact with a thermal reservoir. Now, let me just compute the canonical partition function for this case. Z of C is equal to the integral of e to the minus h beta dq and dp. Suppose that the dimension, since we are in one dimension, we have L, which is the length, or the scale length, the length scale, sorry, over which the particle can move. The particle has just kinetic energy. So the Hamiltonian is just p squared divided by 2m. And therefore, I can compute easily this integral, because the integral over dq basically becomes L. In the case of 3 dimension, we will have the volume, and we will see this example. Then we have the integral over e to the minus p squared divided by 2m beta, and here I have dp, and I have to integrate over all the possible values in dp minus infinity plus infinity. No? We are in one dimension, one particle in contact with the thermal reservoir. So you see that in this case, the partition function for this example is L, and this is a Gaussian integral, which is just pi, and then I have 2m and divided by beta. Okay? So this is the partition function. And now let me compute, for instance, the average energy of the particle. So the average energy of the particle, the average, as I said before, is minus the derivative with respect to beta of the log of the partition function, canonical partition function in this case, okay? So this, which is minus derivative with respect to beta of the log of L. Then let me put here a pi 2m, and then let me take here beta to the minus 1/2. When making the derivatives, let me change page. I can basically neglect the part which is not dependent on beta. Then I have a okay, so let me do the calculation. I need to copy this minus derivative with respect to beta of the logarithm of beta to the minus 1/2. Beta to the minus 1/2. Yeah. Then I have plus a term which does not contribute, because I can write minus derivative of beta. Okay, let me of the log of some factors which do not depend on beta. Okay. So this is equal to 0. And here I have 1/2 and the 1 over beta, which is kBT divided by 2. Okay. What is this? This is the average energy of one particle in contact with the thermal reservoir, computed in the canonical ensemble, and you find exactly the quantity that you expect, which was the fact that a kBT half for 1 degrees of free, 1 quadratic actually degrees of freedom, which is basically the equipartition theorem. Equipartition theorem. So we have 1 degrees of freedom, kinetic degrees of freedom, which is quadratic, and the energy, the average energy associated with these degrees of freedom is kBT half, okay, as usual. So we get a formula that we know. Then, of course, but this we will see later, by applying the canonical ensemble to one particle, I can also derive the Maxwell-Boltzmann distribution, actually, because we said that rho, which was proportional to e to the minus h beta, for one particle is just e to the minus beta times the kinetic energy from one particle which is free, and this is basically the Maxwell-Boltzmann distribution, which allows to determine, for instance, the the distribution of velocity of particles. Okay, but we will derive this later. Okay, so this is the Maxwell-Boltzmann distribution. Actually, we will see how to modify the Maxwell-Boltzmann distribution where we are in presence, for instance, of an external field, which could be a gravitational field, for instance. Okay, so now let me make the story a little bit more complicated, but just a little bit, and consider instead n particles in a volume V, and suppose that those particles are free. And let us compute first compute the canonical partition function for this case. Now, in this case, z of c is the integral. Now let me make it more explicit, dq1 dq3n, because we are in 3 dimensions and we have 3n possible coordinates, dp1 dp3n. Then I have the e to the minus Hamiltonian times beta. And now, since we have some experience with partition function and computation in the phase space, I need to introduce a correction factor, which was 1 divided by n factorial, which was the Boltzmann counting, exactly as in the case of the microcanonical ensemble. And I need to introduce EH to the power of 3n, which is the Planck constant to the power of 3n. Okay, so this is the canonical partition function for a gas of free particles in 3 dimensions, a gas of n free particles in 3 dimensions. And we correctly normalized, we multiplied the partition function in order to have, first of all, the correct dimension. This will be important when computing the entropy, as we will see, and the Boltzmann counting correction that was derived in the microcanonical ensemble. Now, as you see, with respect to the microcanonical ensemble, here the difference is just that I have to integrate over the phase space this function here, e to the power of h beta. Whereas in the microcanonical ensemble, the integration was over a volume, and the difficult part was to find the volume which was consistent with the macroscopic constraints. Here we do not have any constraints on the energy. This is important. Here just the number of particles and the volume is fixed. We do not have any constraint on the energy. However, we are by integrating over all these coordinates and momenta, we are also integrating over the energy. But since we have an exponential here, actually the contribution, as we will see, is basically corresponding to the So the leading part of this integral is provided by basically the average energy of the system. Okay, we will see this in a moment. Now let me go on and compute this partition function. So z of c is equal to 1 divided by n factorial h to the power of 3n. Then I integrate over the coordinates and I get a volume to the power of n. And then I have the integral dp1 dp3n. And here I have e to the minus beta. And here I have the Hamiltonian, which is the sum from I to 1 to 3n of pi power of 2 divided by 2m. Okay? Now, clearly, this integral actually is very easy because this is just this integral here, dp e to the minus beta p squared divided by 2m from minus infinity to plus infinity to the power of 3n. Because the exponential I am in the argument of the exponential is a sum, so basically I have here e to the minus beta p1 squared divided by 2m e to the minus beta p2 squared divided by 2m, etc. And so this integral actually is 3n times the same integral, okay, because these variables are integrated. We are integrated over all these variables, okay? Therefore, this is equal to, as before, to square root of pi 2m divided by beta, which is to the power of 3n, the power of 3n. Okay? Now, we can write then z of c as follows. Z of c is v to the power of n factorial h to the power of 3n. And then I have a 2 pi m divided by k times kbt. So 2 pi m kbt to the power of 3/2 n. Okay, 3/2 n to m pi kbt. Okay, which is also equal to v to the power of n factorial, and here I can write 2 pi m kbt divided by h squared to the power of 3/2 n. That should be correct. Okay, so 2 pi m kbt divided by 3/2 n. Now remember that we define the thermal de Broglie wavelength as h divided by 2 pi m kbt, and therefore this canonical partition function is v to the power of n divided by n factorial, and here I just have lambda to the power of 3n, 1 over lambda to the power of 3n. Okay. Okay. Which is also equal to 1 divided by n factorial, v divided by lambda cubed to the power of n. And this is the canonical partition function for a gas of free particles and free particles in 3 dimensions. It has, of course, it must be a dimensional quantity because, and here you see that we have a ratio between volume and length to the power of 3. Then we have the n factorial, which comes from the Boltzmann counting to the power of n because I have n particles, okay? Now, from this partition function, we can derive all the thermodynamical quantities, and this is a matter of doing an exercise. But before coming to this, or maybe I do this before and then I will derive the other quantity. Okay, maybe yes. Yeah. Okay, let us compute, for instance, the internal energy. It was the average energy, and we said this minus the derivative with respect to beta of the log of z of c before we obtained 1/2 kBt. Here I expect to obtain 3/2 kBt n, because I have number of degrees of freedom which is n times 3, because I have 3 possible directions in which the particle can move, no? And so I expect to have the classical result, which is 3/2 n kBt. And let's see if this works out. So these are minus derivative with respect to beta of the log of, here I have v to the power of n, then I have the n factorial, and let me write plus the log of lambda to the minus 3. And factorial and lambda to the minus 3, and of course I have n here. Okay, now okay, this term will not contribute to the derivative, and then I just have 3n derivative with respect to beta of the log of lambda, if I've done the calculation correctly. Now lambda scales as t to the power of minus 1/2, minus 1/2. This is the scaling of lambda, and maybe I'm doing here, I have to do slowly. Yeah, but I have to derive the derivative with respect to beta. Okay, sorry. Let me change page first of all, otherwise it will mess. Okay. So I get the U is equal to the average energy, and I had the 3n derivative with respect to beta of the logarithm of lambda. And up to this point, I've done the calculation correctly. Now lambda scales as t to the minus 1/2, and therefore it scales as beta to the power of 1/2. And therefore here I have a 3n derivative with respect to beta of the logarithm of beta times a constant k. Okay? And then I have 3n, then I have 1 divided by beta k times k. Therefore this is just 3n divided by beta. Beta. But I think I'm losing something here. Yes, there is 1/2, of course, here. Because it was beta to the power of 1/2, and then I can put the 1/2 there. Okay, and now this is 3/2 n kBt as it should be. Okay, so I get the standard result that I have 1/2 kBt times the total degrees of freedom, kBt half times 3n degrees of freedom. Number of degrees of freedom. Okay, so for one particle I had kBt half in one dimension. For 3 particles for n particles in 3 dimensions, I get 3/2 kBTN. Okay, so this was just a little exercise, then we will do some other exercise, but here I want to do another thing before, which is important. And when we make a break, we can show that actually this relation holds true, which is z of c, so the partition function, is directly connected to another quantity of thermodynamics, which is a function of volume and temperature, which is the Helmholtz free energy. And now we will prove this result, and then we make a break. Proof of this. So basically, what I'm writing here is that 1 divided by h to the power of 3n, let's write the expression that we had before. Here you have a dp dq, which stands for dp1, dp3n, dq1, dq3n. Let me just write dp dq, but I mean the integration of all the possible variables and momenta of e to the minus h to e to the minus h beta. And I'm saying that this is equal to e to the minus beta times a vt. So what I wrote here is written there. Now from this, let me multiply by e to the beta a, and then I get that 1 divided by, okay, this factor here, dp dq, e to the beta a minus h, this is equal to 1. Now what we will see is that actually we will find a relation, a thermodynamical relation, which is correct at the end, and then also the starting point must be correct. Now, one thing that I need to stress here is that A is a function of V, and T is just a function of macroscopic variables, whereas H instead is a function of Q and P. Okay, so only macro variables, whereas here I have only micro variables. Okay. Now let me derive this equation that I call asterisk with respect to beta. And let me change page. When deriving with respect to beta, I have the following equation. So 1 divided by h3n n factorial integral over dp dq. And then I have the derivative with respect to beta of this quantity. So I have the same exponential e to beta a minus h, minus h, a minus h. Then when deriving with respect to beta, the numerator, I have a plus beta derivative with respect to beta of a minus h. Okay, equal to 0. Where I have used the fact that beta, which is 1 over kBt, when deriving with respect to beta, I just need to derive h sorry, A is a function of beta and H is not a function of beta. Okay, let me write, is not a function of beta. Okay, H is a function of Q and P. Okay, therefore I get the following result. Let me put outside the integral all the quantities that are not depending on P and Q. So then I will have, well, basically I will have this factor here, A plus beta derivative with respect to beta of A, times something that is actually equal to 1, because is this factor here, dqdp e to beta this one. Then I have a minus, I will comment in a moment, 1 divided by 3n and factorial e to the beta a, e to the beta a, and then I have dq dp e to the minus beta h times h. This is equal to 0. Okay, let me check if I have done things properly. I have a plus beta derivative with respect to beta of a, which is independent on P and Q, therefore I can put it outside. And then I have this integral, which is equal to 1, which was exactly our starting point. Our starting point, because we said that e to the minus beta a is equal to z of c. Okay, and this is indeed the ratio between z of c and e to the minus beta h. So this is equal to 1. Then let me see what I have here. Now, for the same reason, actually, this quantity here, for the same reason, is just equal to U, which was the average energy. Because I have e to the minus, so beta h at the denominator, which is exactly z of c, which is the partition function. Okay, so I'm averaging h over the canonical ensemble, and I'm dividing by the partition function. So this is just u. Okay, therefore I get the following relation: e plus beta derivative with respect to beta of a minus u is equal to 0 from this equation. Okay, let me compute now this derivative. Now, when doing beta derivative with respect to beta, this is equal to beta derivative of t with respect to beta times the derivative with respect to t. And derivative of t with respect to beta, consider that the beta is 1 over kbt, and therefore t is 1 over kb beta, and the derivative of t with respect to beta is 1 over kb beta squared with a minus derivative with respect to t, which is equal also to 1 minus 1 divided by kb, and here I have I think I'm forgetting something. Sorry. This minus 1 beta squared. Sorry, let me do it more slowly, otherwise I forget something for sure. So this beta derivative of t with respect to beta. Yeah, okay, that's correct actually. Yeah, that was correct. So beta derivative with respect to beta is equal to what I said before, beta. Then I have a minus 1 divided by kb. Then I have a beta squared. Yes. and derivative with respect to t, which is equal to minus 1. Then I have a kb, and I have a beta in the denominator, which is kbt times the derivative with respect to t at t. kb goes away, and then I get finally that beta derivative with respect to beta is actually equal to minus t derivative with respect to t. This relation will be useful in other calculation, so let's try to remember it. So then applying this, let me go on. And then, so we arrived at this point that a minus, so here I had plus beta derivative with respect to beta, which is actually minus t derivative with respect to t of a minus u is equal to 0. Okay. Now, remember that the Helmholtz free energy and the entropy are related by this quantity. So S is minus the derivative with respect to T of A minus derivative with respect to T of A, which is a function of volume and temperature. Therefore, by inserting this into this equation, I get the A minus, so plus Ts minus u is equal to 0, which means that A is equal to u minus Ts, which is indeed the definition of the Helmholtz free energy. Okay, which is correct. Therefore, our starting point was correct because we arrived at the final answer, which is consistent with the definition of the Helmholtz free energy, and therefore the canonical partition function is actually equal to e to the minus beta a, where a is the Helmholtz free energy, and it is a function of volume and temperature. Okay, so this may be more clear now, which is the link between microphysics and here thermodynamics. Because the partition function is computed by integrating the exponential of e to the minus beta h, which depends just on microscopic variables. Whereas in the right-hand side, we have the Helmholtz free energy, from which one can derive all the thermodynamical relations, okay? Now, a similar link between microphysics and macroscopic physics was provided in the microcanonical ensemble. It was the relation between the entropy and the number of microstates. Okay, so the Boltzmann entropy. Also in this equation here, we have here entropy, which is a thermodynamical variable, and here we have a microphysics. Here we have the microphysics content. In the canonical ensemble, we have a partition function, canonical partition function, then we have the Helmholtz free energy instead of the entropy. Okay. Now, as I said before, once we have the canonical partition function, we can compute everything. And maybe we have already computed the average energy, which is the internal energy. Now let us compute, for instance, the entropy. So exercise, compute the entropy for ideal gas. Well, ideal is actually a thermodynamical definition. Here in this case, we just talking about gas of free particles. Okay. Now we said that z of c is equal to minus beta a, from which we see that a, we can compute the log of this quantity and multiply by kbt. Therefore, a is just kbt with the minus log of the partition function. And now let us remember that the entropy, this was the relation that I've used before, is the derivative of A with respect to T. A is a function of V and T, and therefore this derivative, to be more precise, must be computed a fixed volume. Okay? Well, now what we need to do is to use the fact that Z of C is equal to V to the power of n. Then I have the n factorial here, and then I have 1 over lambda 3n for a gas of 3n particles in free particles in 3 dimensions. Sorry. Okay, so it's a matter of doing derivatives here, but let me make it carefully because it's very easy to get lost. So now S is equal, when I compute the derivative with respect to T, I have a KB log of Z of C. And then I have a plus KBT. Then I have to do the derivative of this log with respect to T, which is Z of C derivative with respect to T of Z of C. Okay. Yeah. Where Z of C is this quantity here. Okay, so now this is equal to KB. When doing the logarithm of this quantity, I have n log of V divided by lambda cubed minus KB logarithm of n factorial. Then I have a plus KBT. And here, let me put all the factors there. KBT, then I have, okay, V to lambda 3 to the power of n, and here I have 1 over n factorial. And then I have the derivative with respect to T of this quantity, which is V to the power of n, then I have a n factorial, and the derivative with respect to T of lambda to the power of minus 3n. Okay, so from which I can remove something already. So this n factorial, this n factorials, this V to the power of n and V to the power of n can be removed. Okay, this is equal to kbn logarithm of volume divided by lambda cubed minus, here let me use the standard approximation of Stirling. So this is kbn log of n plus kbn. Okay. Then I have kbt. So I have plus kbt. Then I have lambda to the power of minus 3n kb lambda to the power minus 3n. Then when doing the derivatives, I get lambda to the power of minus 3n 3n minus 1. I think that there is something I'm losing here. This is lambda to the power of 3n. Okay, no, this is plus. Okay, this is a plus 3n. Sorry. Then this minus 3n minus 1 derivative with respect to temperature of lambda. Okay, this should be correct now. And then, of course, I have a factor of minus 3n. Okay, let me check if the calculations are right. kBt, then I have a minus 3n, then I have lambda 3n and lambda. Okay, good, that's okay. kbn log of v divided by lambda cubed minus kbn log of n plus kbn plus kbt divided by lambda, and then I have a minus 3n and derivative of lambda with respect to temperature. Okay, I think I'm almost done. Here I just need to compute this derivative of lambda with respect to temperature, I think. Okay, now lambda is h divided by 2m pi kbt square root. So the derivative of lambda with respect to temperature is equal to h divided by 2m pi kb. Then I have t to the minus 1/2, therefore I have a minus 1/2 and t to the power of minus 3/2. Okay, so this is the derivative of lambda with respect to t. 2 pi minus 1/2 t to okay, good. So then if I do derivative of lambda with respect to t and I multiply 1 over lambda, I should get some cancellation, but let me change page, otherwise make a mess. So those calculations are straightforward but nasty in the sense that sometimes one has to be careful in order not to lose any factor. So I think that we arrived more or less here. So kbn log of v okay, v kbn log of v to the, then there was a lambda cubed. Okay, then there was a minus kbn log of n plus kbn. Then there was a plus kbt minus 3n, and here you have the lambda, which is h divided by 2m pi kbt, and then there was the derivative of lambda with respect to temperature, which is h 2m pi kb. Here I have a minus 1/2 and t to the minus 3/2. Okay, this should be correct. Okay, this can be written as follows. kb n can be collected. I have the logarithm of v divided by n lambda cubed plus kb n log of e. That will be clear for in a moment. It will be clear in a moment what I mean with that. H and H cancels. And here I should have a 3/2n, And let me count the number of temperatures that I have here, 3 half n, kb, okay, is there. And the temperature should drop. Let me see if this is correct, because I have here minus 1 half, so 1 half and plus 1 is minus 3 half, that cancel with that correctly. Okay. Yeah, so then finally I have a kbn logarithm of v times e, and here I have n lambda cubed plus 3 half n kb, and this is the entropy. Okay, kbn, which is the Sakur tetrad formula again. Okay, Sakur tetrad equation for absolute entropy. Okay, that was derived in the microcanonical ensemble by computing the volume of the hypersphere that was consistent with the external, well, or the macroscopic constraints, whereas here is computed directly by doing derivatives of the partition function. Now, to conclude this part, and then we make a break, let's compute also the pressure. Now, the pressure is related to the Helmholtz free energy by this equation, is the derivative of A with respect to the volume at fixed temperature this time. Okay, so this is minus the derivative with respect to the volume of kBt, so this was minus kBt log of Z of C, which was the relation between Helmholtz free energy and partition function. So this is kBt derivative with respect to the volume of the log of Z of C. Derivative with respect to log of Z of C. Okay, which is equal to kBt derivative with respect to volume. Okay, it's kBt 1 divided by Z of C, and then I have the derivative with respect to the volume of Z of the partition function. And this is equal also to kBt divided by, well, this is v to the power of n lambda to the power of 3n 1 divided by n factorial. Then I have to do the derivative of this quantity with respect to the volume, which is 1 divided by n factorial lambda to the power of 3n, and then I have n times v to n minus 1. Okay. So I can remove something. So this drops, and I have correctly kBtn, v to the power of n is removed, so I have pv equal to kBtn. Okay, kBtn kBtn, which is the equational state of for the ideal gas. Okay, as it should be. As you see, I mean, deriving the canonical partition function, once we derive the canonical partition function, all the thermodynamics can be computed easily. Of course, the non-trivial part is to compute the canonical partition function, and we will make some exercise for simple cases. And actually, we will conclude also this part by doing a calculation, by using some approximation, of course, for the case in which we have also interacting particles. But then I think that it's better now to stop for a break. Let's 5 minutes and then we will continue. Okay. Okay, maybe we can start again.
Yes, Prof.
Okay, thanks. Okay, now let's try to answer to the following question now. So why we obtain the same results by using the microcanonical ensemble and the canonical ensemble? Why exactly the same results? Exactly same results for micro canonical and canonical. In the first case, we have considered a system which was isolated. In the second case, we are considering a system which is in presence of a reservoir and can exchange heat with this reservoir. The answer to this question is that actually in the first case, the energy is fixed, the total energy is fixed. In the second case, the total energy is not fixed, but it fluctuates. But the fluctuations are very small. For a macroscopic system, such fluctuations are suppressed. And we will see how much they are suppressed. But to do that, or to show that, we need to do some little calculation. So let me start with this. So Z of C is e to the minus beta A, which was also equal, apart from some constant k, dq dp e to the minus h beta. Where k, it was a constant, a normalization constant that will not be important in this calculation, okay? We will not keep track. We not keep track of k because it's not important. For the following. Okay. And U, the internal energy, we say that this is actually the average over the ensemble of E, and this was dq dp e to the minus h beta h divided by dq dp e to the minus h beta. Okay. Now from this equation, we see that I get the following equation by taking this integral and put on the left-hand side, then collect everything together, and I get the following equation, the integral dq dp of e to the minus beta h of u minus h is equal to 0. Okay. Now let me multiply by e to beta a, this quantity, and let's obtain, and we obtain this, dq dp e to the beta a minus h, and here I have a u minus h, and this is equal to 0. Remember again that a is a function of v and t, whereas u is also a function of thermodynamical variables. Well, in principle, u is a function of entropy and volume, whereas h is a function of q and p, of the microscopical variables, whereas a and u are thermodynamical variables. Okay? Now let me call this asterisk and derive asterisk with respect to beta. Okay? And this, of course, this is equal to 0, and here I have a dp dq e to the beta a minus h which is the derivative, and then I have to derive the numerator. Let me see what how is better to do it. Okay, derive the numerator with respect to beta means okay, derivative of h. Okay, so then I have okay, let me do the following. Sorry, let me do the following. Okay. Okay, let's write in the following fashion. So this derive with respect to beta. So this dp dq, otherwise I get lost. Then I derive u with respect to beta, which is a function of beta indeed. Then I have e to the beta a minus h. H does not depend on beta, therefore there is no contribution to this. Then I have plus u minus h, u minus h, e to the beta a minus h. Then I have a minus h plus beta derivative of a with respect to beta. This should be equal to 0. Let me check if this is correct, just one moment. dp dq, derivative of u with respect to beta, e to beta blah blah, minus h, and a minus h plus beta d beta. Okay. Okay, that's correct. Now let me take this term here. Here you have the u d beta, which can be put outside of the integral because it's a quantity that does not depend on the microscopic variables. Then I have this times 1 because the integral dp dq of e to beta a minus h is equal to 1. Okay, so I just have this term here. Then I have plus integral dp dq of e to the beta a minus h. Then I have a u minus h. And here you have a minus h, and this should be minus t derivative with respect to t of a by using the relation that we derived before. Okay, so let me check if this is correct. Minus h, okay. Okay, now this quantity here, let me change page. So I have 0 is derivative of u with respect to beta plus integral dp dq of e to beta a minus h and u minus h here. Now, if I take a minus h minus t, the derivative of a with respect to t is minus the entropy, so this should be plus ts. Okay, it should be plus ts. And remember that u and a are related by this quantity. So a plus ts is actually u. Therefore, this is equal to u minus h. U minus h. Therefore, actually, here, by inserting this relation, actually I have a u minus h squared. Okay. Now, this quantity is also, so this is telling me that the derivative of u with respect to beta plus this quantity can be interpreted as follows, is 1 over z of c times the integral over dp dq of e to the minus beta h u minus h squared, u minus h squared. Okay. And of course, this can be interpreted as an average over the ensemble of the difference of the square of u minus h. Okay. So then 0 is equal to derivative of u with respect to beta plus the average, the ensemble average of u minus h squared. Okay. Equal derivative of u with respect to beta. Now, when computing the square of this, I get u squared, because when doing the average of u, I just get u squared, plus the average of u squared, of h squared, sorry, which is actually just u squared again, sorry. No, this is the average of h squared, sorry. Then I have a minus 2 u, the average of h. Okay, this should be the correct result. So let me collect derivative of u with respect to beta. Then I have plus u squared plus u squared. Then I have plus h squared average minus 2u squared, because this is just u. The average of h, which is the average of e, is u. Okay. Okay. Therefore, I get the derivative of u with respect to beta plus h squared average minus u squared minus 2u squared is just minus u squared, which is h average squared. Okay. Which of course has the shape of a variance. This is equal to 0, and this is the variance, if you want, of h. So basically, it is the is the deviation. It represents the deviation from the average of the expectation value of the Hamiltonian, or if you want, of the energy. Okay, so from this we get that h squared average minus average h squared is equal to minus the derivative with respect to beta of u, which is also minus the derivative of t with respect to beta times the derivative of t with respect times the derivative of u with respect to t, which is also equal t is 1 divided by kb beta, so derivative of t with respect to beta is I think I've done this calculation already many times, but this is a 1 or minus 1 divided by kb, and then I have beta squared at the denominator, so which means kb squared t squared. So this should be with a additional minus is a kb t squared times derivative of u with respect to t. Kb t squared times derivative of u with respect to t, kb t squared. And so now let me collect this result here. So I have that h squared average minus average of h squared is equal to kbt squared times CV, where CV is the derivative of U with respect to temperature, and this is the heat capacity. Okay, now this relation basically connects the variance of the energy, which of course is a measure of how much the energy fluctuates, and another thermodynamical quantity, which is the heat capacity. Okay, this equation actually is one of one form for what is called fluctuation dissipation equation. Let me write it again. So the variance of the energy is equal to kBT squared CV. Okay. Now, how does scale CV with n, so with the number of particles? This is a specific, well, this is a heat capacity, and therefore is an extensive variable. Extensive variable. And therefore the CV must scale as total number of particles. Think about the ideal gas. For in three-dimensional monatomic ideal gas, the CV is 3/2 nkb. Okay, so there is a scaling in the number of particles which is linear in n. Now, if I introduce f, which is a fractional fluctuation, fluctuation of the energy. This is h squared average minus average h squared divided by average h squared. And let's put a square root because those are squared. Okay. Now it's easy to realize that actually the average of H, which is the average of E, which is equal to the internal energy, and this scales as n, as the number of particles again, as CV. Now, from the previous equation, we get that, therefore, that at the numerator, here we have the variance, and the variance scales as CV. Therefore, the numerator will have a square root of n. Whereas in the denominator, I have a square root of n squared. Okay? Therefore, this scales as 1 over square root of n, which goes to 0 rapidly for n going to infinity. Okay? This means that fluctuations are suppressed for macroscopic system, or if you want, many particle system. And therefore, and which is the suppression? Well, it's similar to the suppression that we obtain in the case of the system. If you remember, the first system, one of the first systems that we studied was a system of spin, non-paired spin, so independent and localized particles with two possible states. and we say that the expectation value of the magnetization was 0 in absence of an external field, and the variance, well, or if you want, the possibility, the fractional occupation number in that case was actually suppressed by 1 over square root of n, so the number of spin. And here we have a similar scaling, so the fluctuation of the energy are suppressed as 1 over square root of n. So that means that even if here the energy is not fixed, because there is a possibility of exchanging energy between the system and the reservoir, in any case, the fluctuations are small and are suppressed by a factor. So they are suppressed with the 1 over square root of n, where n is the number of particles. Okay. Now, since the fluctuations are so small, we get same result in the microcanonical where the energy is fixed, and the canonical where instead the energy is not fixed. There is an internal energy on which we compute, which is an average energy, but the fluctuations are very small. Now, this is a very important consideration, because it allows us to compute, well, to use the canonical ensemble instead of the microcanonical. The use of the canonical ensemble is much simpler with respect to the use of the microcanonical. Because if you think about this calculation here, was a simple calculation in which we had to compute the integral over momenta of e to the minus p squared divided by 2m. It's a Gaussian integral. We do not need here to specify which is the volume of the phase space on which we are computing the canonical, on which the distribution function is different from 0. That in the previous case was a layer, a spherical layer that we actually approximate to the volume of a sphere. In this case, we just have to integrate over momenta, and so the calculation was much simpler, but the results for what concerns thermodynamics are the same. The reason is that, of course, this integral it's easier because we have one constraint less with respect to the microcanonical ensemble. So here we are removing the constraint of fixed energy, and we are just using the constraint of fixed volume and fixed number of particles. So therefore, the calculation in phase space is much simpler in this case. We will see that we will introduce another ensemble, which is the grand canonical ensemble, in which also the constraint on the number of particles is removed, and therefore the calculation will be even more easier, especially in the case of the quantum statistics in particular. Okay, so first of all, motivation for the canonical is that calculations are simpler, especially as we will see in the cases in which, for instance, there is an external field that will modify non-trivially the volume of the phase space in the microcanonical ensemble, and in particular when considering also interactions. Because when considering interactions between particles, calculations in the microcanonical ensemble are basically impossible. Whereas in the canonical ensemble, at least one can proceed with some approximation. This is the first reason. So the canonical is easier to use, and it is justified by the fact that the fluctuations are small. The second reason for using the canonical is physical, well, it is an ensemble which is more, which is closer to a physical situation in which usually the temperature is usually, let's say, systems are not isolated, but at fixed temperature. So it's much easier to consider a system in contact with the thermal reservoir, which is, let's say, a situation which is more occurs more often in physics, instead of considering systems which are completely isolated from the environment. Okay. Let me add another comment about these fluctuations. So we said that h squared average minus the average h squared is equal to kbt squared cv. This is what we derived before. Now, another way to compute these fluctuations is the following. Is actually equal to the second derivative with respect to beta of the log of z of c. Okay. Now, why is so? Why? Let's us compute the derivative with respect to beta of the derivative with respect to beta of log of z of c. Now, this is equal to the derivative of with respect to beta of minus the u average. Sorry, h averaged. Okay, so this is h averaged. And for what we have seen before, so this is a minus derivative with respect to beta of h averaged. And we have just seen before that is minus, of course, this minus derivative with respect to beta of u. And this was actually exactly equal to h squared average minus h average squared. Let me check if the sign are correct. This was anyway derived before, no? Minus derivative of u with respect to beta is is the variance. Okay, and so you see that actually this variance can be computed as a second derivative of the log of z of c. Okay, so if you want, the h average is minus derivative with respect to beta of the log of z of c, and the variance is second derivative with respect to beta of the log of z of c. So again, you see that the partition function basically provides all the things that we need, in the sense that it provides energy, averages, average u, which is actually of h, which is actually u, and also the variance. And one can compute higher order calculations and also have fluctuations at higher order, and so find all the moments, if you want, of this distribution. Okay. But again, the ingredient, the most important ingredient, is the partition function. Okay, in these last 10 minutes, let us make a calculation. Well, an exercise, sorry. Suppose that we have, so this is an exercise, and we consider a system of n particles which feel an harmonic potential. in 3 dimension. So let's suppose basically to have n 3-dimensional harmonic oscillator, if you want, n 3D harmonic oscillators in the, well, non-interacting between themselves. Okay, and we want to write z of c and then to compute u. Okay, so let's try to do it. Z of c is equal to, well, we have the usual normalization factor, which actually will not play any role, but let us remember that in principle we have those factors. Then there is the usual integral dp1, dp3n, dq1, dq3n of e to the minus beta h, where h in this case is a little bit different, and it is the sum of I 1 to 3n of a kinetic part, which will be a times pi squared, plus the harmonic part, which is bqi squared, where a, if you want, is just 1 divided by 2m, and b is characterize basically this harmonic potential, so it's the elastic constant or something like that, okay? Of course, now the calculations is slightly more complicated than the case of a free gas, but actually only slightly, because in any case we have a Gaussian integral over momenta and a Gaussian integral over the position of the coordinates. Okay. So therefore, actually, this can be written as 1 over n factorial and h to the power of 3n. Then, since all these integrals are the same, I just have this. I have a dq as before, dp, e to the minus beta. Then I have here ap squared plus bq squared. And this integral is present 3n times. Okay, so let me check if this is correct. It's 3n dq minus beta, blah, blah, blah. Okay, good. This is equal now to, there are two Gaussian integrals that can be computed easily. So I have 1 divided by n factorial, h to the power of 3n. Then I have a pi divided by beta a to the power square root to the power of 3n. And then I have a pi divided by beta b square root to the power of 3n. Okay? Which is also equal for 52. Okay, now a is 2m. Of course, I will have a part which is basically the same as the case of free particles, and therefore I will just have a lambda to the power of 3n, so a thermal de Broglie wavelength to the power of 3n, which comes from this square root. Then I have an additional factor in this case, which is pi b beta to the power of 3 half n. This term we have now instead, if you compare with the previous case, instead of v to the power of n. Since we have now a dependence of the Hamiltonian on the coordinates, we do not have just v to the power of n, but we have this factor pi divided by b beta 3 half n. And so this is basically the partition function z of c. Now, if you want to compute the internal energy, this is minus derivative with respect to beta of log of z of c, and you will realize that is actually the usual 3/2 n kBt associated with the kinetic energy, or associated with the kinetic energy. And you will have another factor, which is actually just the same, because I have to compute. So, plus the contribution coming from the potential energy sorry, I wrote. Okay, let me change page. The blackboard is much better. Okay, so U is 3/2 n kBt. Then I have to do minus the derivative with respect to beta, minus the derivative with respect to beta of the log of pi divided by b beta. This is to the power of 3/2 n, and so I have a factor here which is 3/2 n. Okay. Okay. Now, okay, this derivative is just 1 divided by pi beta b beta, sorry. Then I have pi divided by b, and then I have a 1 minus beta squared, pi beta beta, so this is just 1 over beta, which is minus 1 divided by kb, sorry, this is minus kbt, okay? And therefore I get 3/2 n kbt plus 3/2 n kbt. Therefore, I have contribution to the internal energy, which is just equal, so the potential energy contribution equal to the one associated with the kinetic energy. Okay, so therefore it's 3 n kBt. Well, basically this was expected because again, for the equipartition theorem, each quadratic in momentum or coordinate term in the Hamiltonian contributes with a factor kBt half. So since we have 3 directions and so 3 momenta, I have this 3/2 n kBt, but I have also 3 degrees of freedom, quadratic degrees of freedom in coordinates that are associated with the 3 possible direction of oscillations of this harmonic oscillator. And therefore, as you have seen, the calculation basically follows the same calculation of just kinetic, the case of kinetic energy. And I will just have just the double just twice the same degrees of freedom that I had before. Okay, basically because the integral is just the same. Okay, so this maybe we will do it next time, but it's already useful. So it's already interesting to see that by using the canonical ensemble, okay, in this case, computing making the same exercise in the microcanonical ensemble was not would be very easy. Also, well, would be actually the same, even in presence of this harmonic potential. Instead of computing the volume of a hypersphere in 3 n dimensions, I will have to compute the volume of a hypersphere in 6 n dimensions in this case. But the formula basically are the same. The difference starts to be clear when the potential are not of quadratic form, because in that case I need to the volume in the phase space of the microcanonical ensemble is more complicated. Okay, so we will see next time that the canonical ensemble, for instance, provide a simple way to deal with simple potentials like this one, this harmonic potential, or potentials like I think we will consider a gravitational potential and a centrifugal potential. And those calculations in the canonical ensemble are, in any case, not very complicated and will be much more involved instead in the microcanonical ensemble. So now it's 1, and I think I will stop here if there are no questions. So if not, I think I'll see you next Thursday.
Ok, thank you.
Bye bye.
Arrivederci, buona giornata.
Buona giornata.
Ok, arrivederci prof.